Hello. Today we're going to talk about comparing three different population growth models and then how to simulate them in Python using ModSim. All right, so we're going to compare three different population growth models today. We're going to talk about the constant growth model, we're going to talk about the proportional growth model, and we're going to talk about the quadratic growth model. Okay, and so when we talk about constant, proportional, or quadratic, these have to do with how fast the population is growing based on the current population. So when we talk about a constant growth model, what we're talking about is that every year the population grows by the same amount. So I'm going to draw two different pictures here. I'm going to first talk about a picture with what this constant growth looks like. So what that is we have a picture where we have the current population, and we can have a picture about the change in population. All right, so what the constant growth model says is that no matter what the current population is, the growth is going to be the same. So if the population is 100 people, they'll have the same amount of growth as if the population is 1,000 people. All right, and then what that leads to in terms of what the population ends up looking like, right? So now this is where the word constant growth comes in. The growth is constant based on what the current population is. If we wanted to talk about what the growth over time looks like, and we have the total population, well, if you start off at a certain amount, then this change in population is going to be constant, so the function of the population will be a linear function. All right, so what we see here is that we have a constant growth, but the population function is a linear function. Okay, so what does that look like, right? So if we have what we did in class is we had some annual growth with some value, and we calculated that as the change in population over change in time. We used we found the total change in population divided by the total time, and we got this value of annual growth. And then we could write a function like the population in 1951 is equal to the population in 1950 plus this annual growth. And then the population in 1952 is equal to the population in 1951 plus that same annual growth, and etc. Population in 1953 is equal to the population in 1952 plus the annual growth. And so what we're seeing here is that the annual growth is staying constant. No matter what the current population is, the change in population is the same constant, and that leads to a linear growth over time. All right, so now let's compare that to a proportional growth model. So a proportional growth model says that every year the amount of births and deaths is proportional to the population. Okay, so let's draw what the graphs look like there. So we have a graph with the change in population as a function of the current population. All right, so what this proportional growth is saying is that if there are 10 people in your 10 people in your city and you have 1% growth, well, that's taking 10% and it's adding one person. But if you have 1,000 people and you take 1% of that, you would add 100 people. So what this is saying is that the amount of births and deaths are proportional to the current population. Now, with this type of growth, you would expect the population to increase exponentially over time. All right, and so you start out with some initial population and then you grow and you increase exponentially over time. So one thing that could be confusing is that in the constant growth model, the population function is linear. But in the proportional growth model, the change in population as a function of the current population is linear. So I will be using the words constant growth model, proportional growth model, and it's important to talk about constant growth or proportional growth and comparing that to the actual value of the population function. So in this case, the population function is exponential. All right, and in this case, well, let's look at what that looks like. Well, so the population at time 1951 is going to be equal to the population in 1950. But now the number of people, we have some birth rate. Why not call that BR? And we have a death rate. We'll call that DR, maybe just B and D. So the birth rate is B, the death rate is D, and so if we start out with a current population of population 1950, and then we add in the number of deaths, which is B times the current population, and subtract off the deaths, D times population, 1950, well, we get that the population of 1951 is equal to 1 plus B minus D times the population at 1950. All right, and similarly, the population at 1952 is going to be 1 plus B minus D times the population at 1951. And then the population in 1953 is going to be 1 plus B minus D times the population of 1952. Right, and this is giving us a mathematical way to see that it will actually be an exponential growth because every year you're multiplying by the same factor. Right, if 1 plus B minus D is greater than 1, then you'll be increasing over time. If 1 plus B minus D is less than 1, then you'd actually have exponential decrease. Okay, so now let's talk about quadratic growth. So in quadratic growth, every year the amount of the amount of net growth is a quadratic function of the population. Okay, so here, let's go back to the proportional growth model. The net growth is this amount that's changing. This B times population minus D times population. This is a linear function of the current population. And what we're saying here is that the amount of net growth, so if we're going to write our chart again, change in population as a function of the current population, well, what's going to happen here is we've got a quadratic function. All right, and so what we're saying here is that at the beginning, when there's a small number of people, this is increasing. It gets to some maximum rate of change based on population, and then it decreases over time. Right? There's a good reason for this. So there's a good. It's more complicated than a proportional or constant growth model, but it's probably a better model of the way populations grow, which is that at the beginning, when resources are not constrained, in this area, we've got population increasing exponentially. Right, so it's increasing as if it's increasing exponentially. The resources aren't a limiting factor, but as the population grows and grows, this change in population is going to start to slow down, and at some point here, there's going to be too big of a population. If you were to be too high, then too many people, this is too many people, or too many uh, uh, animals in this population would lead to population reduction. Right, so if we were talking about how this would look as a function where we have the population over time, well, it's going to have the same type of behavior where it's going to increase kind of exponentially, but then as it gets higher and higher, the growth gets smaller and smaller, and so it levels out at some limiting value. And this is called a logistic curve. So when we have a quadratic growth model, then the population function is logistic. Right, and so what would this look like? This would look like the population at time 1951 is equal to the population at 1950, right? It starts off with the same, with the previous population, and then we add some net people. So that looks like, so plus the net growth. And so in this case, the net growth is going to have some alpha times the current population. This is the first of the linear term. And then there's some beta times the population in 1950 squared. Right, so what is this? This is a quadratic growth model where the next population is based on a quadratic version of the current population. All right, and similarly, the population in 1952 is going to be equal to the population in 1951 plus alpha times the population in 1951 plus beta times the population of 1951 squared. And then we can do that again, population of 1953, etc. Yeah, alpha population of 1952 plus beta population of 1952 squared. Sorry about that mess. I'll be trying to be more careful as we go. All right, so let's talk about how we take this and we would put it into a simulation. Okay, so in order to put this into a simulation, so creating the population simulation, all right, we're going to be using the same setup that we talked about last class. All right, the way we do that is we need a system object with system parameters. And this is model dependent. So different models need different system parameters, but we need to create the system object that has system parameters. We need an update function that updates the population at time t up to time t plus 1, depending on those system parameters. And we need a run simulation function that takes in both the system object and the update function. And it outputs the results of the simulated population. All right, so as we had in class, we have to define this run simulation. We'll define run simulation of system and update function. And we create this time series, results equals time series. Results, we're going to initialize it. Results of the first time, which is system dot t0 equals system dot p0. And then we run the loop to collect the data for t in lin range of system dot t0 up to system dot t end. We need to do the following. We need to run the update function and collect the information. Results of t plus 1 is going to be the update function of results of t, comma system. And then we're going to return the results. All right, it's going to output the simulated population. All right, and so let's now compare our three different models. So in our three different models, we had a constant growth model. And for the constant growth model, we needed our system object. We need to have the initial time. We have to have the end time. We have to have the initial population. And we need to have the annual growth. And these are our system variables. And the way the update function works here, so if we define the update function for the constant growth for a population given the current time and the system information, well, it's going to return the population, current population, plus the system dot annual growth. All right. So that's the constant growth setup. For the proportional growth, well, in that situation, our system variables need to have t0, t-end, p0, and then we need the birth rate and the death rate. So these are the system parameters. the system variables that need to be in the system object, and we're going to define the update function for proportional of population t system. And so what does that do? Well, it's going to take in, let's define the number of births to be equal to the population times system dot birth rate. We're going to define the deaths to be equal to the population times the system dot death rate. And then we're going to return the population, the current population, plus the number of births minus the number of deaths. All right, and now let's talk about the last one, which is the quadratic growth. All right, for that one, I'm going to switch this up a little bit just to fit it on the paper. Well, we need to have our t naught, our t end, our p0, and then we need our two different variables, alpha and beta. And then when we want to define the update function for the quadratic growth that takes in the current population, the current time, and all the system parameters, the system variables, then we'll define the net growth to be equal to system.alpha times the population plus system.beta times the square of the population. And to do that, you do population star star 2. And then we return the population plus the net growth. All right, and that is how we program those into Python. So I will make sure that we have a Python notebook that does all those things for you. And that is what we wanted to cover today. All right, I'll talk to you later. Bye.